Hi, good afternoon. So this talk is last talk at the RubyKaigi, this RubyKaigi first day. So today I want to talk about the progress report of the Ractor system on this year. I'm Koichi Sasada from Stores. So today I want to talk about some implementation for some important feature implementation for Ractors. So two features, the require and timeout. And also I will show you some survey, some analysis about the memory management on the Ractor system, and show some future plan. So I'm Koichi. So let's introduce myself again. So my name is Koichi Sasada, working on the stores. So I'm very happy to be here this year again. And I'm author of Yellow Virtual Machine and some garbage collector, Debugging, Ractor system, and the thread scheduler system. And also director of Ruby Association. So let's start today's talk. So Ractor was introduced from Ruby 3.0, and it's designed to enable the parallel computing on Ruby. So Ruby has threads, but threads doesn't run in parallel on CRuby because the parallel computing with threads will introduce some critical bugs or something, so critical things. So I don't want to introduce such a thread programming hell. So we designed Ractor system with robust concurrent programming. So this robust feature nature makes the no bugs parallel computing because of the no object sharing or very limited object sharing. However, limiting the such a object sharing between Ractors, so we need to introduce some strong limitation to the Ruby language. So we separate all objects into the unshareable objects and shareable objects. And so most of Ruby objects, string, array, or most of user defined class and modules instances are unshareable objects. And also we have some special shareable objects. So immutable objects or some special objects such as a class, modules, and Ractor objects themselves. So because of this, so we define that the shareable object can be shared with between Ractors, but unshareable object cannot be shared between Ractors. So so this is a simple rule, but to keep this simple rule, we need to introduce many strict rules. For example, we can't define the constants containing the unshareable objects. So if so for example, there is no example. So large C equal string is a very common Ruby program. But a string object is not a shareable object. So the main Ractor means that the startup Ractor, only the startup Ractor, main Ractor can access to the constant C, but other non-main Ractor, so we call the child Ractors. So child Ractors cannot access to such a constant C. Also, the same reason, global variables are prohibited to access from child Ractors, and so on. So, because of such strict rules, we lack many important features like require or timeout or blah blah blah. And also, we observe the very critical performance regression on memory management. And maybe there are many other issues. So today I want to show you how to enable such important features on Ractors. So the require, at first I want to show you the require issue. So the current Ractor system couldn't require any features on child Ractors because require access to the global access to the global states, and also many of features violate some violates the Ractor rules, such as assigning the unshareable object to the constants. So, because of this situation, we prohibited the require from child Ractors. However, many of cases we need to require on child Ractors. For example, so some methods require some features on the method. So, for example, PP method, you don't need to require anymore. Maybe after Ruby 2.5 or 4, I forget the correct version number. But the PP method requires the PP library at the first calling timing. So, because of this limitation from child Ractor, we can't call PP. So it is too bad to make some programs. So, and also, of course, outload is issues. So first time of the accessing to the constants, require some feature for some constants. So outload. So if we want to support the outload, we need to allow the require from child Ractors. So, but there are some issues like that. So the conclusion is we need to support require from child Ractors, but all of require should be run on main Ractor. So to enable the require method on child Ractor, at first I want to introduce a new method, Ractor interrupt exec method. So this method invokes the expression on the receiver Ractor. For example, the Ractor.main returns the main Ractor, interrupt exec with the block. So this method interrupts the main Ractor, the main thread, and run this assignment to the global variable on main Ractor. So this method runs the expression on the receive Ractor's main thread asynchronously. So it means that the method doesn't wait the result of the expression between block. So this method is very powerful feature. So we can make many systems on this method, but this method is also danger because it is same as a trap handler and sending a signal. This interrupt exec also interrupts some kind of blocking IO calling, like a signal handler. So for example, we call the read method. So read method need to wait, for example, network streaming. But signal calling, sending a signal, it interrupts such a read method, and calls the trap handler. After trap handler was called, then restarts the read system call. So the interrupt exec, so proposed interrupt exec method do same thing. So this figure shows how to work on the two Ractors. So at first, the child Ractor calls this method. Then stop the main thread. Sorry, main Ractor's main thread, and run the expression. And after that, the restarts the main thread logic. So called child Ractor doesn't wait to the result of expression. So after calling this method, so the rest of logic are run. So using this interrupt exec, we can make a Ractor.require method. So using the Ractor.main interrupt exec, calls create a new thread and require on the main Ractor and wait to the result. From the child Ractor, the child Ractor need to wait the result of the require from main Ractor. So the thread is needed to avoid double locking or deadlocking. So this diagram also shows what happens on the Ractor.require. So at first, child Ractor calls this method and runs the block on the main Ractor. Main Ractor restarts the main Ractor's logic just after creating the thread. And on the new thread, requires a feature and returns the result to the child Ractor. So for example, most of the case, require will success. So it returns true or false. But sometimes it can raise an error. So load error, there is no such a feature or some exception in the code. So we need to check, we need to know what kind of error can be, was raised. So we need to wait the require result by our child Ractor. So we prepare the Ractor.require. So we need to use this method from the kernel Ractor. The kernel require. So the kernel require simply run the Ractor.require if the current Ractor is not a main Ractor. So we only need to add this line on the original require. So I think there is no problem on this logic, but there is some feature because some libraries override our require method. For example, Ruby gems, Bandler, and blah, 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 more and more libraries because they want to do some additional feature on require method. So if we change the kernel require, but the overriding library doesn't have the effect of this. So override method need to call the Ractor.require. So this line. But I'm not sure we can ask all of require overriding author to write this one line on their library overriding require definition. So another solution is to introduce a new module to check such a feature, such a guard, and prevent the kernel with the new Ractor-aware require module. So it's fine because the prepended methods are called at first. However, another problem is always the ancestor tree contains this Ractor-aware module. So I'm not sure it is accepted or not. But just now, I can introduce some idea, so we can discuss how to merge it after that. So this is not about the Ractor, but Ractor require, but about debugger. So Ractor interactive exec or the thread interactive exec can be a key feature for the debugger. So just now, at the breakpoint, we stop all of thread with the trace point, but we can't stop the IO blocking threads or something like that. And also, we can't stop all of threads in other Ractors. So just now, the debugger doesn't support Ractor anymore. So I believe that this feature, interrupt exec method, is a good feature to implement or to support the Ractor system for the debugger. But this feature is dangerous, like a trap handler, because it can be interrupt any code. Any code means that the cleanup code can be interrupted. So it is the same danger with traps signal handler. So I'm not sure this feature can be accepted easily, but I like this feature. So another feature I want to introduce is timeout. So current timeout mechanism is creating a one timeout monitor thread, and the other thread ask that the sender the exception when the 1 second or the timeout second are elapsed. So this communication flow is only on the thread system, and the child Ractor cannot communicate with this timeout monitor thread in the other Ractor. So the current timeout method is not supported on Ractor. So the simple solution is making a timeout monitor thread for the power Ractors. So for example, there are two Ractors and make two timeout monitor threads. So it is easy, and so I can implement it in 30 minutes. However, so if we have thousands of Ractors, then the timeout monitor thread can be thousands timeout threads. So it is not good, not ideal. So another solution is design new communication paths to asking the child Ractor to this main Ractor timeout monitor thread. But it is just now it is difficult. So back then, last year I showed this presentation slide. So to make MN threads, we introduced a timer thread. Timer threads manage timer events or I/O interrupts or something like that. So timer thread is native thread. So we can use the timer thread as a timer native thread monitoring system. So the main Ractor and other Ractors can ask the timer native thread to register and unregister the timeout events. So this is not concluded API design, but this timeout exec method accepts the second, and what happened on the timeout is occurred. So with this feature, we can make a timeout with between the Ractors. So using this timeout new timeout, then the timeout method. So most of the timeout doesn't raise a timeout error, but only do the register and unregister by the timeout monitor threads. So I make some benchmark. So doing the null task. Null task means 0 seconds task, so there is no timeout. So I repeat this one 1 million. And on the thread or on the solution ones, the power Ractor timeout thread system take 5 minutes, but the native system, the solution 3, only take 3 minutes, 3 seconds. So it's faster, but not so faster. So I check the reason why it's not such a faster, because the accessing to the hardware clock is too slow. So I use another API, so course model. So it allows some errors, so up to the 4 milliseconds. But it is enough for our purpose. So I choose this API, and it is about 2 times faster. So I think it is good performance improvement, I think. So last 5 minutes, I want to show some GC performance issue. So this is so I always show this example. So making the 50,000 Ractors, and send a message to the next Ractors, and the next Ractors, and the next Ractors. So it make a ring. So we can measure how much time is needed to go around this ring. So with MN threads, so we can see the 70 times faster or 6 times faster with GC disable or GC enable. So we can measure the good performance with MN threads on Ractor system. However, creation time, we make 50,000 Ractors with GC enable and also measure the GC disable. So with garbage collector, it's too slow. So compare with the MN thread, non-MN threads and MN threads with MN threads, it is slightly faster, but very slow than with the GC compare with the GC disable and GC enable. So this is of course it is an issue. So so after the analysis with about that, so we can observe that too many garbage collection because of the page tuning parameters. And also, the stopping active Ractors, we need to do garbage collection. So the Ractor system, the one garbage collection is slower than the non-Ractor system programs. So to confirm the result, so I prepared a very simple task. So making the n Ractors or n threads and do this task. So this task is simply make 100 arrays. So it make many garbage collection. So the results should be proportional to, the task of the total task is the proportion to the n. So the result should be same or faster, should be faster on Ractor system. But with the measurement, so with Ractor, the execution time is proportional to strongly correlated with the GC count, and the GC count is clearly increased from the non-Ractor system. So with threads only consume only counts this GC counts, but with Ractor system, so it takes so many GC counts. So after the analysis, we observed that so for example, there is 3 pages with 4 Ractors. So Ractor 1, Ractor 2, Ractor 3 caches each pages. And then Ractor 4 want to make a new object. So Ractor 4 need to allocate another page. However, there is no new page. So there is some empty slots. So with threads, we can make more and more objects without garbage collection. But there is no pages, no other pages. So then run the garbage collection and allocates this page for Ractor 4. And after Ractor 1 want to allocate the page, this one, and this one. Ractor 2 allocates another page. And Ractor 3 need to allocate a new object. Then there is no pages. So need another garbage collection. So it is not this is accidentally occurred. So we need to tune to. So this is accidentally. So we need to fix this situation. And also we need to stop all of Ractor to run the garbage collection to make traverse, so there is no mutation. So there is no conclusion for the garbage collection, but after this kind of observation, we need to aware GC tuning, Ractor aware GC tuning, and Ractor local GC to run the garbage collector each other. Also, this presentation proposes some new methods. So we can implement the require and the timeout method. And also, we want to improve more and more for the memory management system with Ractors. So I hope you can wait some minutes or some years. I'm not sure, but we want to improve the situation. Thank you so much.